If you go to Blackboard and go to your course evaluations, I think you can judge both of us on there. Do you know how that works with both of the courses? Do they have to go to your course specifically for that?
Oh, that's a good question.
That's a good question, huh?
Yeah, I might have to open up my course if that's the case.
Yeah, because I think the one that's going through the Math 138, Math 1330.
Okay, I will
13,
open up
14,
my course.
Math 138.
But there's nothing in my course except that evaluation. So
Okay.
I wonder if I can link the evaluation to our course. Anyway, I'll see it. I didn't know. I don't know.
Yeah, she might have to open up her course, but if you go to the Blackboard and you go to course, I think it's under course evaluation link, you should be able to give us a review on how we were doing on the class. And so they're going to ask you a few questions and then maybe like rate this on a scale of 1 to 5 or something like that, I think is what they do. So with that, you're pretty much free to, and it's done in anonymity, so you're pretty much free to say and do whatever you want on those things. Some people go pretty wild, some people go, about accurate, but are there any questions over anything we've done so far? I think last week we took a test. We talked about exponents. Or hopefully you watched a video about exponents. Is that where we're at now? There was a lot of Thanksgiving. Okay, so yeah, it was a short week. So yeah, we pretty much just took a test right before the break. And then hopefully there was a video that you watched over exponents, because today we're going to go over exponential functions. And then tomorrow, you're going to also need to know exponentials, because we're going to go into logarithmic functions. And everything we do with logs, we're going to sort of define it with what we're doing with the exponentials. So 5.4 is really based off of doing the opposite of what we're doing in 5.3. But in order to do the opposite, you got to know the original thing, right? And so I guess there's not a whole lot of questions because we just took a test. But maybe you watched the video, maybe you have questions over the video, over exponentials. Was there anything in the video that you have questions over? If not, this is a fairly lengthy section, I think. Oh, we got these homework problems. So 14, 15, 41, 43, 55, 61, 70, 75, 79, 96, 103, 109, 113, 123, and 133. Okay, so we're looking along here and they want us to look at these two tables. So we want to see these things numerically and be able to determine whether something is an exponential or a linear function. If we're looking at the axes and how the axes are going up, they're going up by +1 each time. So hopefully that is something you notice, but it is, they set it up in a sort of nice way, right? They're not trying to do anything too confusing here with the x's. If we look at 14 and 15, if we try to set this up with what? A linear. If you try to set it up, what operation would you be looking at to do between these two things with linear? Is that a weird, maybe that's a weird way to ask it. But what's the operation? Like if we were going up linearly, we would be looking. Could you repeat that? I barely caught that.
If it was linear, we would also be adding, wouldn't it?
Yeah, you would be adding and looking for a slope. If you add a number here, what would we have to add? 6?
Mm-hmm.
We add 6, does that get us to the next thing?
No.
No. So right away, you can tell me this is not linear, right? Hopefully.
Yes.
So you're not adding the same number. But if we're looking, and I ain't got much room here, so let me throw another piece of paper down underneath. If it's not linear, that's a pretty good indication. It's probably exponential. What would we have to go by to get from here to here? What's the operation if it's exponential? It's not adding, it's got to be
Multiplying.
multiplying. And if you had to multiply by a number, what would you multiply 2 by to get to 8?
4.
You multiply by 4. And if we multiply by 4 each time, does that get us to the next number?
Yes.
Okay.
Wait.
So we wanted to find a model that works for this. So we know it's exponential. The thing I'm thinking of is my basic exponential function. It should look like some kind of coefficient with a base to my variable x. So this is the like general form of a exponential function. So there are two things that I need to fill out when I do this thing. I need to fill out my c, and I need to fill out my a. And I can get both of those from this table. This table is set up in a sort of like pretty way where I could hopefully grab these things out. So I talked about C in the notes. C is like another way of saying what? What is that talking about?
The x-intercept or y-intercept, right?
Yeah, like. And so if I want to fill out C, what is the number I want to put in place for C? Hopefully you're looking along here. That's my y-intercept.
So 2.
I can fill out 2. Do you want to do a little bit more work just to like see it for yourself? If you want to plug in what 0 is my x and 2 is my y, this is also why I'm saying your C is always going to be your y-intercept. Because if we plug in 0 to my x, what is that going to happen? What's going to happen to my a?
It'll go away.
Yeah, it's going to equal 1, right? So anytime you're talking about your y-intercept, your a is going to sort of like, I want to say disappear, but disappear is not really a proper math term. It's going to simplify out to 1, right? And so c equals to 2. Another way you can get that is by plugging this point in. So if you have to plug this point in to see it, that is fine. If you can just go and grab, say, hey, c is 2, that's fine with me as well. The other thing I want to talk about here is the base. The base of a, where am I getting that thing from? And if you want to plug in numbers, you can plug in numbers and kind of justify it to yourself. You could go a to the first equals 8, something like that, right? But I think we can just grab it from the table if you notice this pattern. What is the number I'm going to want to put for my a?
4.
This is the rate of change that is happening. So I want to put 4, and this is what? 2 to the x. So the 2 is coming from the y-intercept. The 4 is coming from this rate of change, multiplying by 4 each time. So each time I increase my exponent by like 1, I should be multiplying it by another power of 4 is another sort of way to look at that. So y-intercept, and this is like your rate of change. What do they call it? Multiple of change. Okay. I did that one. I want you to look at this next one. It's a little bit different. It's like they cranked it up 1 notch to 11. We are going up 1 in the x each time. That should hopefully not be the thing that's confounding you, right? What what I want to do is look along here. So first off, is this linear?
No.
It is not linear. If we were looking here, we're going to subtract 32, and then I think we're subtracting 16 or subtracting 8. It's going to change each time. We're not going to get a constant amount. So I want to think about this, and it might be a little weird, but I want to think about this as multiplying. From here to here, here to here, here to here. I want to think about this as multiplying. You might think about it as dividing. And if you were to say it's dividing, you'd say this is dividing by what number?
2.
Dividing by 2 is the same thing as multiplying by? Yeah.
1/2.
By a half. So this is the sort of thing, multiply by the reciprocal. And if we look along here, is that going to simplify, or is that going to solve each one of those inputs? 64 divided by 2 is going to give me 32. 32 divided by 2 is going to give me 16. It's going to give me 8. It's going to give me 4. It looks like it should work for all of them. Okay. Now, hopefully, we can fill this thing out. We know this is a linear, sorry, not linear. We know this is an exponential function. I need to fill in 2 things to this thing. I need to fill in my C. I need to fill in my A. What is my C value there? Where am I getting that from?
0 and 8.
I'm
So
getting
8.
from this point 0, 8. If I plug in 0 here, this is going to give me 8. My A is going to sort of disappear. My C is going to be equal to 8. Now I want to talk about my base. What is the base here? What is the rate of change that's happening?
One half.
It is 1/2. And this looks like to the X happening here.
So what makes the X go on the inside or outside of the parentheses?
Yeah, I was noticing I was being kind of sloppy with that, probably, right? It probably should go on the outside if I'm being honest. It doesn't matter too much here because it's just 4 to the X. It's not a fraction, but I should have probably really written it as that 4 being raised to the X.
Okay.
It's just with this here, it's probably, I think it looks a little prettier if you do the 1/2 in the parentheses to the X. It just, it keeps you from maybe getting 1 to the X over 2 or something silly like that. I don't know. Being able to distinguish this thing from this thing, right? We don't, that's too much. I don't know what to say. Like it's too easy to mix those things up. So
Yeah.
I should probably really put the X on the outside of the parentheses. Because then I can look in here, I can see my bases of 1/2 is the rate of change I'm talking about. I can look out here, I can see my y-intercept is 8. And so it should probably go on the outside. I was probably just being lazy, and I'm glad you like brought that up. Because I thought about it as soon as I started doing the 1/2. I was like, yeah, that's probably confusing there. Okay. So this is how we find it from a table. Our C is coming from the y-intercept. And the rate of change is giving us our A or our base. We want to do what? 41 and 43. We're skipping 42. So now they want us to find a C and A so that we have a exponential function. The models the situation describes. State the variable X. State what the variable X represents in your formula. So there are initially 5,000 bacteria, and the sample doubles in size every hour. And then the other one says in 2015, a house is worth $200,000 and it decreases by 5% each year thereafter. So these are a little bit tricky, if I'm being honest. That one of them is. I feel like the first one might be a little more straightforward, maybe. For the first one, we're going to have a exponential model. And so we talked about what sort of exponential models look like graphically, and the notes we talked about that. But they should look sort of like that. And so I'm drawing it beyond probably the axis that I need it. Because it's going to happen mostly in the first quadrant if we're talking about something in reality. And so it's going to go towards like 0 here. It's going to grow, and it's going to grow exponentially, right? Sometimes we use that word exponentially to mean like drastically. Like it's almost interchangeable in like everyday language, right? You're like, it's growing exponentially. It just means it's growing drastically, right? So exponential functions, they grow really quick. So the question, if we start with 5,000 bacteria, what is that sort of like giving you? If this is my model.
That would be your y-intercept.
That would be like your y-intercept. So we're starting up here at 5,000. So at time 0, my y should be 5,000 is what that is telling me. They are initially 5,000 bacteria. And the sample doubles every hour. So I'm hoping you have this picture. And so if I want to find an exponential model, there are 2 things I really need to find in my exponential model. One of them is the C and one of them is the A. And so I think we have enough information to fill this thing out. What is my C value here?
5,000.
That's the 5,000 that we're starting out with. That's like your y-intercept. That's the initial value you start out with. When your x or your t is 0, this is the value you're going to get. The other thing is my base. Now I want to talk about this base. What are they telling me this thing is doing? It is doubling. So how do I do a double? What does that mean?
Multiply by 2.
You're multiplying by 2. And so this should hopefully be the thing that you're getting here, right? This is coming from your y-intercept. So when we did linear functions, your y-intercept was kind of like your starting point or your initial value. It's the same thing here, right? It's still your starting point. That's not changing. These weird guys over here may be changing a little bit, right? We're multiplying, so now it's going to be a base with an exponent. Instead of an mx, right? We get a to the x. So it's a little different, a little wonky, but hopefully it's manageable. All right, so 43. This one's a little trickier. Although we did do compound, like a compound interest problem in the notes that might help you set up this sort of thing. Okay. So on new f of x equals c a to the x. So I think the easy thing here to maybe to pick out from the problem is hopefully your c value. So if we want our C or our y-intercept, what is that going to be? What is it starting out as?
200,000.
It's starting out as 200. This thing might be a little tricky. So it's going to decrease by 5% each year. So if we take 5% off of something, and we want to multiply, this is the part that's a little weird.
Didn't we discuss this earlier in the semester though? About 100% increasing and decreasing from, maybe not.
I'm not sure. If a shirt is on sale for 5%, how much of that shirt are you going to pay for? If you get 5% off, you're paying
95%.
95% of the shirt, right? And so it's kind of similar. We wanted to take 1 or 100%, and we want 5%. You can think about this as like 100%, and we're moving 5%. Or 5% away from 100%. 9 is 95% of something. I think we did something kind of similar when we did compound interest, but we go up when we go compound interest. Here we're taking away 5%. But the two things you should be getting from this are what? The C value is the 200,000. And if I want to reduce something by 5%, I'm paying 95% of. So that is where I'm getting my C and my A from this word problem. Okay. And so now we want to do which ones? 55. 43 was that last one? Yeah, 55. Are we not doing 51? Did I skip one?
Next thing's 55.
Okay, yes. Okay. 55 and 61 is the next one. I was double checking these numbers, make sure we got them all.
You better do that.
I thought they lined up. I was like, it seems like we got 4 of them there. I felt like I should have been doing one of them, which I probably still should, but we'll do 55 and 61. What do they say? Sketch a graph of these things. So if we have to sketch a graph, what do you probably want to do with this? I got to get some points.
Plug in numbers for X.
Plug in numbers for X. So I would create a table to graph these things. I'd plug in a few negative numbers. I'd plug in maybe a few positive numbers. I would probably just go from -3 to +3 if I'm being honest for this one. Okay, so you're gonna have to know about negative exponents. So if I do 3 to the minus 3, what is that going to give me? Let's do 3 to the 0. Let's do that one. That one's always really fun. If I do 3 to the 0, what is that going to give me?
Zero.
Ooh, 3 to the 0? What does that give me?
1.
This gives me 1. If I do 3 to the first, what is that going to give me?
Three.
Yeah, okay. If I do what? 3 squared, what is that giving me? And 3 to the third, what does that give me? What's 3 squared? 3 and 3 is going to give me 9.
9.
And another 3 is going to give me. So if I go 3 to the minus 1, what does that give me? Or 3 to the minus 2, or 3 to the minus 3? Three to the minus 1 is like what?
1 over 3 to the first.
1 over 3 to the first. It's like 1 over 3. What is the negative do?
It goes away.
Yeah, so this is like 1 over 3 squared or 1 over 9, right? Same thing here, 1 over 3 to the third, or like 1 over 27. So going back to this good old exponent rules that we talked about a while back, if we have negative exponents, you can flip it over 1, make it positive. You might notice the 1 over. So we get these numbers. We want to plot these numbers. Do you think you could plot these and graph them? So hopefully you can fill this thing out knowing your exponent properties. Oh man. And at some point I said like, hey, we're going to use and reuse the stuff we're going to learn here. And it's going to come up again in the future. I wasn't trying to say that just to be mean. Like we really do that. So minus 3 is going to give me a little fractional amount. And it's a little fractional amount here each time. I get up to 1/3 right here, I think. Not even a half. And then I get 0, 1. I get 1, comma 3. 2, 9. And then at 3, I'm already off the graph. So I'm plotting these points on my graph. What this graph should look like as it's going to the left, it should look like it's got an asymptote. Cross this line. So it's kind of horribly drawn because I should be getting closer and closer, but pretend like this gets closer and closer and doesn't hit the asymptote, right? This thing is moving this way in some direction. And so as my exponent gets more negative, I get a smaller and smaller fraction, right? Is what I'm sort of saying. It's never going to hit 0. It's going to get really close, infinitesimally close, but it's never going to hit that 0. If we want to look at the domain of our exponentials, the domain is all real numbers. So we can plug in anything negative, we can plug in anything positive. If we want to look at the range is be a little bit weird. It's going to not include 0, but it's going to go off to infinity here. Are there any questions on this one? So hopefully that seems like a fair sort of thing to do. If you've had exponent properties before, you should be able to plug this thing in, plug in these numbers and evaluate them. If you evaluate them, you should be able to draw the graph from the points. Now we get this one. That is not the prettiest one to do, but I think it is manageable. 2 and a 1/4 to the x. Yeah, I might just want to do 1 and 2. Okay. I think just doing 5 of them is probably good enough on this one, I think. If we plug in a 0, I think this is the easiest one to probably plug in. What is that going to give me?
Two.
It should give me 2. So how are we getting 2? Plugging what? F of 0 equals 2 to the 0. So we do 1/4 to the 0. This is just giving me a big fancy one. This is where we're getting the 2 from. There are a few ways you could fill this out, if I'm being honest. You could look at the 0, 2, and you could go by a rate of what? 1/4. If you wanted to do that, that's absolutely a way you could do this. If we want to fill it in, you might notice we get what? 2 times 1/4. Multiply by 1/4 to get. You could do 2 times 1/4 would give you 1/4 would give you 1/2, right? And we can multiply by 1/4 each time if you wanted to do and notice this pattern here. This is one way you can get. The other way is to actually go and plug them in like I started to do here, right? So you can either plug them in or you can notice the pattern and work off the pattern. If I want to work off the pattern, I know I'm multiplying by 1/4 to get here. So how would I go backwards?
Multiply by 4.
I would multiply by 4. So this would give me what? 8. 8 divided by 4 would give me 2. If I want to go backwards, I would have to multiply by 4. All right, so I got a few points I can plot here. And maybe you might want to notice, but this one was like a 3 to the x. And so we talked about what's going to happen if your base is a whole number that's greater than 1 versus if it's a number between 0 and 1, like a fraction. But what is this graph going to do? This one went up. What do you think this one's going to do? We can plot it. -1, 8.
Go down.
It's going to go down. So if we do -1, 8, we do 0, 2. We do 1 1/2. And we do 2 1/8.
Crossing.
to the x, and y equals 3 to the x. To the x. So this would be exponential increase. This is what decay. Okay. And so maybe it's worth pointing out, but negative exponents are sort of like we flip them over, right? One. So if you really want to be crazy, you could probably look at this as 4 to like the -1. But these are related, right? If we talk about 4 to the x, to the x. If I talk about 4, 1/4, kind of like 4 to the. So this is sort of like I'm taking this thing and I'm flipping it about the y-axis. So if we look at these two things, increase versus decay, right? They're related by a factor of the negative in the exponent. If we put the negative in the exponent, we're flipping about the y-axis. Increase and decay relate by like some sort of symmetry about the y-axis. Here, as we go off to the left, we get that horizontal asymptote of y equals 0. Here, as we go off to the right, we get that same asymptote, right? So we get the same asymptote, just in a different direction. We get the increase going off to the right, we get a increase going off to the left, or we get a decrease if we go to the right, right? So it shoots off to infinity in the opposite direction, right? And it goes to the asymptote in the opposite direction. So our asymptote and our infinity kind of get flipped. Okay. $55, $61. Oh, is it? It's getting warm here. Hold on. Okay. I have some kind of crazy mechanism hooked up to my hot water heater for my apartment. I don't know what sort of mechanism it is, but they have to come switch it out. So I'm just like fanning out the oven right now, just heating my apartment off the oven. So it was getting warm. I forgot I had it on. Starting to sweat. And it ain't just the math. I was like, ooh, this math is getting hard. No, it's just the oven's on. So where are we at? We are on 55, 61. We did 61. Next thing we are doing is 70 and 75. So now we have a graph. We want to find C, we want to find A. So I'm hoping right away you look at this thing, you can tell me what C is. What should my C value be from this graph?
Three.
That is the 3, that is that y-intercept that is happening there. All right. So it might help if we table. That might help you. If we go 0 and we go 1, 0 is going to give me 3, 1 is going to give me 1. Should my A be? How am I getting from here to here? That's the question, huh?
Dividing.
I'm dividing by
3.
which is the same thing as multiplying by
1/3.
1/3. So my A is
1/3.
1/3. And maybe you want to do like some sort of mental check. If we plug in x equals 0, are we going to get 3 out of this? I think we should. 1/3 to the 0 is going to give me 1 times 3 is going to give me what? 3. That should check out. If we plug in 1, I'm going to get 3 times 1/3. Is that going to give me what back? 1? I think it does. It should check out. Okay. So again, C is our, what does C represent?
Y-intercept.
Yep, just in case you didn't get it by now, our C is our y-intercept. They are one and the same thing. If we plug in a 0 here, my A is going to disappear, so to speak. It's going to turn into 1. I'm just multiplying by 1. I'm talking about my y-intercept. My A is the rate of change. So I have to see what is happening between consecutive points. It looks like I'm dividing by 3, which is the same thing as multiplying by 1/3. So we want to think about things as multiplication. Okay. And so 75. It wants to talk about modeling phenomenon. And it says match the situation A through D that models it best. I'm not the biggest fan of this one. I feel like they should have made these lines a little more curvy, but it's okay. It's like they try to contrast with this as linear, but they gave you the same example. We're pretending like these are exponential, I think is what we're doing, even though they don't look very exponential. The balance in account after X years earning 10% interest compounded continuously, or the balance in account after X years 5% compounded annually. And then we have air pressure in a car with a large hole and air pressure in a car with a pinhole. All right, so if we look at 1 and 2, if you're talking about the balance in an account, is it going up or down?
Up.
It's going up. If you're talking about air pressure in a car that's got a hole in it, that is going
Down.
down. So for 1 and 2, I think we should either be getting what? B or D? Just a second. Yeah, y'all can come in if you want. Fine. All right, so if we're matching the situation with the graph, the balance is going up, so it should either be B or D. If we're compounding continuously and it's 10%, or if it's 5% and compounded annually, we want to look at which one would be faster. So if we're looking at these two, which one of those should be increasing quicker?
The first one.
It should be the first one that's 10%. 10% is, and it is getting compounded more times per period, right? And so the more compounding you do, the larger it should be. The larger your interest rate, the larger it should be. So what I am saying is that this one looks like probably number 1, it's going off faster. And this one looks like it's probably the second one. Okay. So if we're talking about air pressure in a car tire with a large hole versus a small hole, decrease faster, right? The larger hole is going to decrease faster. And so we're using our skills to basically deduce which one this is, right? So if it's the one decreasing faster, I think that's going to be, I believe that one would be that one. So I think there's basically two questions you're asking yourself, and you can use kind of the power of deduction, right? If it's going up or if it's going down, and then which one's going up faster, which one's going down faster. All right, so that's what, 75? All right, so we're going through 79 now. They give us this graph f of x equals 2 to the x. They want us to sketch a graph of each equation using transformations of graphs and reflections. Do not use a graphing calculator. So they want you to do these things without doing a table. You should be able to sort of take this graph and move it up, down, left, or right, or flip it and get the resulting graph. So 79, they want us to do A, C, and D, I think. So not B. Okay, so we got 3 graphs. All right, so we have 2 to the x minus 2. Ooh, it's small. A 2 to the minus x. And then we have a minus 2 to the x. Is that what they have? Okay. And if they write it like this, it's sort of like that negatives on the outside. We're going to do a 2 to the x, and then we're going to tack a negative. So if we take a 2x minus 2, we're going to take this graph, and what are we doing to this graph?
Move it to the right 2 times.
Okay. A minus 2.
Moving it down.
That. This would be moving it to the right 2. If the minus 2 is attached to the x, if it's in the exponent, then that would be moving it left to right. So if it's out in front, if it's not in your exponent, this would be moving it down 2 units. So I'm glad someone said that. So now we can look at both these sorts of things, right? All right. Do y'all see the difference between those two things and what I'm saying?
Yes.
Yes, if it's in the exponent itself, then it's left or right. It's like right here with that x. Here, it's like we're doing the 2 to the x before we do the minus 2. So since we're doing this thing last, it should be moving this thing down 2. So all we're doing is taking this thing. And one thing to notice, it's got a horizontal asymptote here at y equals 0. If we move it down 2, guess where that thing's going to be now?
Negative.
Should be along here at this negative 2, right? So we should be getting that asymptote. We should be getting the point 0, 1, but now it's going to be moved down 2. And so it may be important to grab that point. If I'm being honest, I'm not going to be too picky with the rest. This is trying to see what graph transformations look like. So if you move that thing down 2 and got it pretty close, got this one point and here your y-intercept, I think that would be pretty good for me. I'm not going to be too picky about all those points if we're just doing graph transformations. Okay. So now we have what? Y equals 2 to the minus x. So what is this going to do? And you don't even have to tell me how it goes. What is this minus? What does a minus do when you throw a minus on something?
Reverses it.
It's going to reverse it or flip it, right? So we're going to do a flip. And what are we flipping? What
Uh,
quantity? What quantity is this flip on?
The X value.
It is on the X value. So this X, our X values get flipped. So if we think about flipping these X values, we're flipping these over here and we're flipping these over here. We're flipping these X values. What are we going to flip about?
Y-axis.
This is a flip about the Y-axis. So again, I kind of went over this in a silly way, but we could actually also think about this as 1/2 to the X. And sort of going like X properties. 1 to the X is another way to think about this. Maybe -1 times X will get me back to that minus X. I could probably think about separating them like that, maybe. -1 is just another way to write a half. Like 1/2 to the X. That might be another way to think about this. But it's like I'm taking 2 to the X and I'm flipping it about the Y. And last but not least, I'm going to take a 2 to the X and I'm going to put a negative on the outside. What is this going to do to my original graph?
Flip about the X-axis.
About the X-axis. Flipping the Y quantities, we are going to flip about our X-axis. So instead of 0, 1, I'm going to get the point, I believe, 0, -1. Instead of it getting closer and closer here, I guess I can draw my original graph on here. It might be the easiest. This is my original graph, something like this. I want to flip that about the X-axis. Instead of up here, I'm going to this is going to be and the negative direction. Okay. Oh man, did I tell you that stuff we learned before is gonna come up again? Yeah, okay. So if they tell you to graph something out, there are a few ways to do it. We could do it by doing a table, right? We did it by doing a table in the previous problems. The other way is by graph transformation. So if you're doing a table, I obviously want you to plot your points that you have on your table or get them pretty close. If you're plotting a fraction, you're going to have to kind of guesstimate where that fraction is a little bit, right? But for the most part, you should be plotting the points that are on your table. If we're doing something like this with graph transformations, I'm probably going to be a little less strict with like getting your points all correct. It's like I'm going to take this original graph and I'm going to do certain things to it. As long as you're doing the correct thing to it, I think that's mostly what I care about. Whether you're moving it down to, or whether you're flipping it about the Y-axis, or whether you're flipping it about the X, right? I care more about like what you're doing to it than getting each little tidbit correct, right? You should probably get the y-intercept in there, at least, for your exponentials. That y-intercept is a pretty defining point. And it's not too hard to find on most of these, right? Might have to do a little bit of thinking, but I think it's manageable. Okay, so where are we at next? We want to do 96 and 103. Use the compound interest formula to approximate the final value of each amount. Okay. Oh man, do I remember the variables that they use in this one? That's a good one. Amount equals principal 1 plus my APR. that what they use in this book? So this is if we have interest compounded once per year. Ms. Watson, do you make them memorize these formulas, or do you give them to them on their test? You're on mute. It looks like she'll probably give them to you if she expects you to use them. That's usually what I do. Yeah, I don't expect y'all to memorize these. This is if it's per year. I don't even think the book gives them this.
They just have to know when to use them. What I do is I just put the formulas at the top of the page, and then they have to
I
know
hope
when
I'm getting my variables right on this, because my other book uses slightly different variables. The same thing. But this is if it's compounded once per year. Ooh. That's important. If it's not compounded once per year, I have to convert my interest rate to whatever the compounding period is. And then I got to change this to reflect the total compounding periods. And then if it's continuously compounded, you got to get your hair silky sheen with that PERT formula there. So a lot of people memorize this with the PERT formula. That's a shampoo. Few people caught that reference when I made it. So I think it might be going out of style, but they still make it. It's called PERT Plus. But these are the formulas that they give us. So if we're looking at an account that is $3,300 at 3% compounded quarterly for 2 years. If we're looking at these three formulas, guess which one you're going to want to use for number 96.
The second one.
1, 2, or 3? I'm going to say number 2. All right, so I want you to attempt to plug in those variables. This is just plugging stuff into a formula at this point, I think. Can you read that problem and tell me what goes in where? And then after you do that, there's a little bit of order of operations, but I don't want to speak too soon, but I don't think it's super complicated here too much. All right, so that's 96. I want to look maybe ahead at 1 or 3. This says it is compounded continuously. Can you guess which one you're going to use there? What's the key word they use? Okay, that's the key word. What does that tell you to use?
The third one.
The third one, the PERT formula. You want your hair to be continuously silky smooth. Use your PERT formula. All right, so I want you to plug things in. I want you to plug things into these two formulas. I want you to try to do some order of operations. And I want you to do a calculator check on that one of them, probably. Both of these, probably. So it's kind of a calculator check time. So A equals what? 3,300. I do 1 plus my rate over N. Okay, so one thing you do have to do correctly is you do have to convert what, 3% to a decimal. Hopefully you're doing that correctly. If you do convert 3% to a decimal, what variable is that 3% giving us? What are we plugging that in for?
The R.
This is my R. Or 0.03. My P is my principal, which is what?
3,300.
3,300. My N is the number of compounding periods, which is what here?
4.
4, because they tell me quarterly. Quarterly means 4 times per year. And then the only other thing I need to plug in is my T, which is what number?
2 years.
It is the 2 years, the time of 2 years. So hopefully, when you plug things in, it looks like this. From here, we have to do some order of operations correctly. But we're doing what? 0.03 over 4. Give me 0.0075. So I need to divide this thing. You can multiply your exponent if you want to do that. 4 and 2 will give me 8. I have to divide to add this thing. It would be easy because you have 1 plus a fraction. Should give you 1 in that fraction. This thing is your calculator check time. 1.0075 to the 8th power. If you can do this in your head, you're doing better than I am. I don't know what to tell you on that. You're doing some crazy math. I don't know why you're in this class. 1.0075 to the 8th. And then you multiply it by what? 300. Approximation, but I don't approximate things. I just let my calculator go. And if I'm doing this, I should really round it to 2 decimal places. 3502. And that is because I'm talking about money here. So what is this telling me? Like, step back and assess what this is really saying. If I put this amount of money, 3,300, in at 3% compounded quarterly for 2 years. So I'm starting with 3,300 in this account that has all this sort of properties to it. I'm going to end up with what? 3,500. Does that make sense?
Yes.
And I'm going to end up with that after what? 2 years? At 3% interest. Does that seem about right? I mean, you can kind of like, guesstimate these things a little bit, right? We're not expecting something to be like $10,000 after 2 years, right? At 3% interest. Hopefully you have a little bit of like experience with accounts and things. Your bank account just isn't going to blow up overnight, right? You might get a little bit of money added there. That's like what, $200? That seems reasonable, right? I just graded my other classes test. It was all over like this this accounting sort of stuff. So I've seen all sorts of things. But sometimes doing a mental sort of check on like what you're talking about is this is a good sort of strategy. So the other thing, I didn't plug everything in here. I want to use the PERT formula for 103. So I already messed up because I didn't plug in my P. My P is what, 1,500? My E is the Euler's number. This thing is a bit of a booger. That is 0.75%. If we want to convert this to a decimal, what does it look like as a decimal?
Uh, 0.0075. You move it 2 spots to the left.
Yeah, I got to move that 2 spots to the left. This is my R. I'm plugging in this to my PERT formula. So I'm looking here. My P is the 1,500. My R is the 0.0. And I got to multiply that by my T, which is 8. So 0.0075 times 8 is probably the first thing I want to do. I want to multiply these. And now I'm looking at e to the 0.06. So this thing I'm going to have to do in my calculator. I don't know any other easy way that you're going to do that besides with the calculator. 1.0618. And I'm multiplying this by what, 1500? Without rounding, I get 1592. And rounding it to 2 decimal places, 70.
Does everyone know how to get to the E on their calculator?
Okay. So the E on your calculator, and I think I mentioned this in the notes, but it should be opposite of ln, of the natural log. This is the natural exponential or Euler's number. When we talk about logs and talk about inverse operations, we'll talk about the natural log. So it is not the same as the capital E, and we talked about capital E and that being scientific notation.
And Euler's is spelled EU, not OI. That's why E. I think, isn't that why E is the way it is? E is for Euler.
E is for Euler. I
Yeah.
used to like always mispronounce this guy's name for the longest time.
Euler.
Euler, yeah. Euler. Sorry. It's not Euler. It's Euler as in like the Houston Oilers. But yeah, sorry.
It wouldn't look very good in an alphabet book, though. It's kind of funny because it's not pronounced like it looks.
Yeah, it's. He came up with some crazy identities. If you ever look at Euler's identity, it connects like imaginary numbers to sines and cosines, trig functions to what is it, e to the I pi, right? It's got pi in there too.
E to the I pi, isn't that 1?
E to the I pi plus 1 equals 0. What is this? I can bring it up right quick. No. E to the I pi plus 1 equals 0, I think is Euler's identity.
Oh, there we go. I knew there was something that had all those important numbers in there.
But you can also do it with sines and cosines. You can start throwing cosines and sines in there with the trig identities. E to the ix equals cosine of x plus I sine x, I think is what he did.
Oh, yeah.
So if you want to be really annoying, or e to the I pi is another way to do it. E to the I pi equals cosine pi plus I. You definitely come up with some crazy identities. Definitely not expecting you to memorize these crazy things. But like it's really weird that he relates several different fields, right? We talk about e's in this section. We talked about i's and imaginaries in previous sections. We talked about pi's, cosines and sines. We haven't even talked about, that's trig, right? So he's like relating all these different sort of things that we learn in these different areas of math, and he's all relating them in this one identity. And what you will find out if you go and study math and like higher math is this stuff happens all the freaking time. Like you will study and study everything about imaginaries in this one section. You'll study and study stuff about trig functions over here. And then you'll figure out, hey, these two concepts, they relate. And it's just like this mind-blowing thing where like worlds collide in math. And it happens pretty frequently. It's like, oh man, all that stuff I was doing over there, I can use on this. It's like, yes, you can. This stuff, like it really becomes applicable at that point. Those epiphany moments, right? That's what I'm here for. So bacteria growth, we have a few modeling sort of problems left, 109, 113, 123, and 133. So just a few more modeling problems. A simple bacteria taken from a river has an initial concentration of 2.5 million bacteria per milliliter, and its concentration triples every week. We want to find an exponential model that calculates the concentration after X weeks. So they want us to say, call it b of x, but it's going to be an exponential function that looks like ca to the x. So there are two things we need to ask ourselves. What is c? What is a? We need to fill those things in.
C is 2.5.
Okay. And put in 2.5, but just remember it's like million bacteria per milliliter is the units on it. That's fine. A is going to be
3.
3 because it time we're going to multiply by function that models this. We take our y-intercept, our starting point is 2.5 is where we're starting. We're tripling it, so we're multiplying it by 3 each time. Okay, now estimate the concentration after 1.5 weeks. So we can build our model. Now they're going to want us to evaluate something with our model. Okay, so now the thing we need to ask is, what are they giving us? If they tell us 1.5 weeks, is that giving us an X value or is that giving us a B value?
X value.
It is giving us an X value of equals to
1.5.
we do have to make sure they are weeks and weeks, right? So we do have to make sure this says 1.5 weeks and this says weeks. So our X variable, we made it in 2 weeks. We also have to make sure this isn't the same thing. If they told us days or something, we'd have to convert it to weeks. But you do want to make sure they are in the same units. So this is what we're doing. We're plugging in 1.5, so we're doing 2.5, we're doing 3 to the 1.5. We're plugging in 1.5 and we're seeing what this thing gives us. So 3 to the 1.5, I think, is the first thing I should be doing. For this, definitely going to need a calculator to figure what the heck this is. 3 to the 1.5 should be giving me something like 5.196. Somewhere in that ballpark. So I'll probably round it on there, but I'm not going to round it till the end of my thing. So I should be getting somewhere around 12.99. It's pretty close. And now they asked us a problem with words. We should probably give them a response in words. So what is this telling me? There are 12.99
million bacteria after 2.5 weeks or 1.5 weeks.
bacteria. Careful. Bacteria per 1.5 weeks. Okay. It is 10:20. If you got to get going to places, you can get going places. I think there are, what, 3 more examples we got to work through. All right, so we have 3 more examples. So these are pretty similar to something we've done before, I think, for the most part. A stock is worth $40 a share and it decreases 2% per week. I want to do my exponential function. What is my C? What is my A here? I'm going to find my model for this thing. What is it starting at? What is the y-intercept value of this thing?
40.
The stock value of 40 decreases by 2% each week.
Starting point is 40.
Yeah, the starting point is 40. What is my A here? So this might be a little tricky. But if we're decreasing by 2%, what is my A? And we talked about this in the previous one, but if it's decreasing by 2%, if you have something on, yeah, if you have something on sale by 2%, what you're doing is you're paying 98% of that thing, right? If we take 2% off, we should be left with 98%. And so this is my general formula. Now they're asking me what happens after what? 6.5 weeks. So what am I doing there?
X is equal to 6.5.
I'm doing X is equal to 6.5 is what they're telling me. And so I'm plugging in what, 40, I'm plugging in 0.98 to the 6.5. So if I do 0.98 to the 6.5, that gives me somewhere about 0.8769. And if I multiply that by what, 40, 35 point where? Oh, 8 if we round it up, I think is what we're getting. Okay. Are there any questions over how we set this thing up? So this is like the 100 minus 2% happening in here, right? This is the amount we're starting out with. They're going to give us a value for X to plug in. They could give us a value for Y, but they can't do that in this section technically. Not until the next section we start doing logs can they do that. And we start back solving. I don't think that's going to come up until we just start doing logarithmic and exponential equations, to be honest. So here, they're probably going to give you straightforward, give me an X value. I'm going to plug it into my function, figure it out. Where are we at? 123, modeling traffic flow. Cars arrive randomly at an intersection with an average rate of 50 cars per hour. The likelihood or probability that at least one car will enter the intersection with a period of X minutes can be estimated by that thing. That is blurry as heck. Is what that thing says. Find the likelihood that at least one car enters the intersection during a 3-minute period. So what are they telling me? What should I do on this? And it's pretty verbosely worded. Like it's like a lot of words there to tell you to do something pretty simple. What am I plugging in where?
Plug in 3 to the X.
They're asking you to plug in 3 to the X. They're saying X is the number of minutes and P of X is giving you some sort of probability. And so they're saying, well, what is it when it's 3 minutes? So what we do is we plug in 3 to our X. I'm doing 1 minus e to the minus 5 times 3 over 6. This is 1 minus, this is e to the what? Minus 15 over 6. Minus 5/2. I think we divide that by 3 top and bottom, right? If you wanted to maybe simplify your fractions, you might be able to do it. All right, so we got to do e to the what? Minus 5 over 2. Or if you didn't reduce it, you could do minus 15 over what? 6. So calculator check. If we do e to the minus 5 over 2 or e to the minus 15 over 6, even if we don't reduce it, our calculator should give us the same result. So one thing is to make sure you have a negative in the exponent here, right? Make sure you're throwing that negative in the exponent. Don't get rid of it. I would just evaluate it as it is. So we have 1 minus this 0.082. So if we subtract 1 from that answer, it's giving me 9179. Okay, so we didn't talk about probability in this class, but what does probability mean? It's another way to give, basically, you could convert this to maybe a percentage, might make more sense. 91.79% would be another way to look at this probability. So probabilities are basically percentages, but we convert them to decimals. So we go from 0 means 0%, 1 means 100%. And we look at how close it is to either 0 or 1. Either 0 meaning it's not going to happen, 1 meaning it's kind of guaranteed. And so this is a 91% chance. There's another way to look at this. It's a pretty good chance. Okay. Questions about this? Do you think you can plug in a number and evaluate it in a function like this? Do you have some sort of technology that will allow you to do this, right? So this is a sort of calculator check. And 133, the last but not least. Chlorine is frequently used to disinfect swimming pools. Chlorine concentration should remain between 1.5 and 2.5 parts per million. On a warm sunny day with many swimmers agitated in the water, 30% of the chlorine can dissipate into the air or combine with other chemicals each day. Find C and A such that linear function models the amount of chlorine in the pool after X days. Assume that the initial amount is 2.5 parts per million. Woo. What is my C value? What am I starting with?
2.5.
The initial amount is 2.5 parts per million. So my C value is 2.5. What about my A? Now my A might be the thing that's a little weird. On a warm sunny day, swimmers agitate in the water, 30% of the chlorine can dissipate. So if 30% is going away, if we get a 30% off sale, how much of this thing is going to be remaining?
70.
70%. And if I want to write that as a decimal, that looks like what? 0.70. So if they want a function, I do believe this is the function that we're coming up with. So they're going to ask you to find a function, or maybe they don't ask you to find a function and you still got to find it. Then the next part, guess what they're going to do? What is the chlorine concentration after 2 days? So that 2 is like a what value?
X value.
It is definitely like an X value. This is like I'm plugging in X equals 2. So F of 2 equals 2.5, and I'm doing 0.70 to the 2. I do 0.7 to the 2, that's 0.7 times 0.7, 0.49. What is this? 2.5 times 0.49. I'm getting 1.225. And that's in what? Parts per million? Parts per million. And what are they talking about when they say like parts per million? Are you familiar with that unit?
That's the number of molecules of something out of every million molecules.
Yeah, exactly. They're talking about the number of molecules, the number of atoms that are in that guy. Exactly. And that is what, the final one, I believe. All right, so I'm just going to go ahead and reemphasize this. We're doing logarithms tomorrow. In order to do logarithms, you really got to have the sort of grasp on these exponential functions. We are going to base a lot of that stuff we do on logarithms off of these exponentials. So I like really want to emphasize, like, go home, get this stuff down. And it's like it's some of it's kind of redundant. You're kind of already home, but I'm used to teaching in person, so I don't know what to tell you. Go home and get this down. If you're already home, look, you're already one step ahead. Yeah, look at there. All right.
Make
so
sure
that,
you watch the video.
that is it. Yep.
Okay, thank you.